So chapter 5 kind of extends what we were talking about in chapter 4. Chapter 4 was all about bonding, how we get those molecules arranged together to form compounds out of elements. Chapter 5 is kind of the process where we make chemical reactions take place. And so in a lot of ways, it is the methodology for how we go about getting these compounds to form in the first place. So we've talked about how they form. Now we're going to get into the actual nuts and bolts of how we make them appear. So in order to do that, we need to understand some basic essentials of chemistry from the standpoint of chemical reactions and equations. So when it comes to a chemical equation, we can kind of think about chemical equations as kind of sort of the story of the chemical reaction. In a chemical equation, we have a substance that is reacting, or substances that are reacting. We call them reactants. They exist in our chemical equation on the left-hand side of the arrow. And we have our products, the substances that those chemical reactants reconfigure themselves to form, and they're kind of the end of the reaction. And we find those on the right-hand side of the arrow. So in our chemical equation, we are seeing a transition from reactants to products. And the reactants and products are separated from each other by an arrow. And that arrow indicates the direction of the reaction. Now, some other information that we can get out of a chemical reaction itself. Oftentimes, chemical reactions will be given to us with states of matter next to them. So that's what these are: S, L, G, and AQ. S, probably guess, stands for something in the solid phase. L refers to something in the liquid phase. E refers to something in the gas phase. And AQ stands in for something that we refer to as an aqueous phase. Off the top of your heads, anybody give me a good definition for what aqueous might mean? What does aqueous sound like? What are those first three letters? Okay, yeah, the first three letters are AQU, aqua. Aqua, we know, means water. So we know that the aqueous phase has something to do with water. What might it have to do with water? Yeah, that's exactly right. We're talking about something that is dissolved in water. So all that stuff that we just talked about in chapter 4 about polarity and solubility, ionic compounds, polar compounds, when those substances are dissolved in water, we refer to them as being aqueous or in aqueous solution. And so those are the four primary physical states that we are going to run into with this particular course and where with this kind of viewpoint of chemistry. If we see phases, they are going to be one of these four. Now, there are other phases that do exist, but they're a lot more specified. And generally speaking, we're not going to encounter it. So before we get into the balancing of chemical equations, it's actually useful, or at least in my mind, to be able to classify those chemical reactions. Because if we can classify them, we actually stand a much greater chance of being able to balance them correctly, because there are certain things that are associated with each of these 5 types of reactions that we can then turn around and use in a practical way in the balancing process. So there are 5 primary types of chemical reactions. There is what we call the synthesis reaction. Synthesis reaction sometimes goes by another name. You sometimes see it referred to as a combination reaction instead of synthesis. The 2 words basically mean the same thing. Synthesis means putting together. Combination means putting together. So we're going to see in those kinds of reactions, we're going to be putting together reactants to make the product. And if that sounds like, well, that is not just every kind of chemical reaction, not quite. We'll get into the differences and distinctions here as we go. There are also decomposition reactions. Those are reactions that are going to result in a molecule kind of breaking apart. We have replacement reactions where we see different components of compounds switching places, replacing each other, and we can break them into single replacement and double replacement based upon the kinds of products that form. And then we have everybody's favorite reaction, the combustion reaction, where, well, that one's kind of self-explanatory. This is usually where we find things on fire. So those are our 5 reaction types. Let's get a little bit into the details of each one. So here's a combination reaction. In the combination reaction, what we are seeing as the defining characteristic, we are seeing the formation of a single product formed out of multiple reactants. So in general, we are going to have some combination of reactants coming together to make this one single product. Now, what those reactants are can vary a lot, as shown by our examples here. In our examples we see in the first one, we've got elements, hydrogen and chlorine, turning into hydrogen chloride gas. In that example, both of the reactants are elemental. In the second reaction, we've got sulfur trioxide reacting with water to make sulfuric acid. In that particular reaction, both of the compounds, or excuse me, both of the reactants are compounds. So we're taking smaller compounds and bringing them together to make a larger one. And obviously, there are examples of combination reactions where we have the 2 coming together. Elements and compounds reacting with each other to make a new substance. Okay, so we'll get to what that means in a little bit. That'll probably be Monday's lecture. But what we're talking about there is a form of balancing the equation. If you notice, there were 2 hydrogens and 2 chlorines here in the reaction, but the product only had 1 of each. That 2 tells us that those other 2 atoms didn't just float away and disappear. They also reacted and formed another molecule of hydrogen chloride. So what it means is that there are two molecules of hydrogen chloride there, not just one. And so that's going to be kind of the basis of what we get into when we talk about balancing equations. Is the primary reason we do it is to account for every atom that reacts, to make sure that we have none that are left over, or that we don't have any extra on the product side that worked on the reactant side. That's why balancing equations exist. That's why it's important. The decomposition reaction. Notice that the decomposition reaction is kind of the reverse of the combination reaction. In this reaction, what we have is a single reactant breaking down into multiple products. And again, the format of what those products look like depend on what the reactant is. Those products can be elements, as is in the case of this first one, where we have water breaking down into hydrogen and oxygen, or they can be compounds, like the case here, where the magnesium carbonate breaks down into magnesium oxide and carbon dioxide. Both are extremely possible. One thing about all these that they all have in common, though, is that these always will require some kind of energy input, whether it is heat, which we will often see given by the Greek letter delta, or shock, or electricity. Some kind of input is going to be required to break the bonds in that compound to get it to decompose. So in the case of this first one, water splitting into hydrogen and oxygen, this actually occurs with electricity. You know as well as anyone that if you heat up water, it doesn't split into hydrogen and oxygen. If it did, you might have a potential problem with your gas stove as you're boiling water to make your spaghetti. But it doesn't do that. It just boils it off. Turns it from water in the liquid phase to water in the gas phase. To get water to split, to break those bonds in water, we got to shock it with electricity, process known as electrolysis. With magnesium carbonate, on the other hand, just gently heating it will cause it to decompose. And the products of that decomposition are magnesium oxide and carbon dioxide. Which have some kind of important effects. Carbonates are actually very common in use in fire extinguishers, dry chemical fire extinguishers. Because what happens is as you spray that dry chemical onto the fire, the heat of the fire causes the carbonate to decompose. When it decomposes, it creates a solid that can blanket the fire, and carbon dioxide to create a gas barrier to choke it out from oxygen. So both of those things happen. That's why dry chemical extinguishers work. Replacement reaction. Now, I said in the introduction here, replacement reactions occur when we have basically components of the reactants switching places with each other. And so we can see in this reaction where that has occurred. Element X here has decided to kick element Y out of the compound. And now we've got element Y by itself and a new compound of X and Z. What makes this single replacement is that we only have one compound on each side of the reaction. So if we look at our examples here, we've got the compound nickel 2 nitrate. Magnesium kicks out the nickel, makes magnesium nitrate and nickel metal. We've got iron and copper 2 sulfate. The iron kicks out the copper, makes iron 2 sulfate and copper metal. Most commonly, we see single replacement reactions in this context, with metals kicking out other metals. But it is possible to see nonmetals behaving similarly. So take, for example, a reaction here between sodium bromide and chlorine gas. In that reaction, the chlorine will kick out the bromine, and we'll end up with sodium chloride and elemental bromine, Br2. So it does work on both sides, but most of the examples you see will be of metals because there aren't nearly as many nonmetals that are capable of doing this kind of reaction. Mainly we see it just with halogens, the B7A compound. Double replacement, on the other hand, here we have two compounds on each side of the equation. And what we're going to see is basically these are ionic compounds, and we're just going to do some partner switching. So A and B are both positively charged ions. In a double replacement reaction, they will switch places. So double replacement reactions, there's a couple of things that we could and should know about them. First of all, we can recognize them by the fact that we see the switching of places. We also should recognize them as double replacement because there will be two ionic compounds on each side. And we generally see this with ionic compounds when they are dissolved in water. So these reactions here, if we were to put phases on them, you can see this is aqueous, this is aqueous, this is actually a solid that comes out of the aqueous solution, and that is aqueous also. Sodium fluoride, aqueous, aqueous. In this case, all of the products are aqueous. Big difference there is that the hydrogen fluoride is substance mass. Even though it's not considered a strong acid, it's a very highly reactive one. It is reactive to the point where it does not, you can't store it in glass. You'll eat through the glass. You have to store it in specialized polymers like nalgene that are corrosive resistant. Hydrogen fluoride, when it vaporizes, is actually very dangerous to you. It can react with the calcium inside of your body and form little spots of calcium fluoride that your body has a hard time processing. Taking enough of it basically calcifies you. Die. But again, you can see in each of these examples, the partnership. Silver, nitrate, sodium with chloride, silver, sodium with switch, silver now with chloride, sodium now with nitrate. Sodium with chloride, hydrogen with chloride, sodium with hydrogen with switch. Now sodium with chloride, hydrogen with chloride. We start with 2 compounds, we end with 2 new compounds, and nothing has changed in terms of the makeup of the substances other than we have swapped ions. No, that's an illustration. What I was trying to show there is these all occur in solution. You're not going to find these kinds of reactions occurring much anywhere else. All right, last type of reaction, combustion. Again, this is stuff catching on fire. And more often than not, what is catching on fire is we've got some sort of hydrocarbon substance, combination of carbon and hydrogen. Now, the thing that all combustion reactions have in common is that they all share oxygen as a reactant. What happens in all of these reactions is we have oxygen as a reactant, and that oxygen is going to oxidize the product, or excuse me, the other reactant. What we'll see is that oxygen is going to insert itself into the components of that other compound. If we're dealing with a hydrocarbon, that means that we'll end up getting carbon dioxide from the reaction of carbon and oxygen, and water as a result of the reaction between the hydrogen and oxygen. So each of these first 2 examples show that relationship. There are other substances that do burn other than hydrocarbons. A couple weeks ago, we talked about ammonia. Ammonia has flammability, although it's not in the range considered by the DOT. But oxygen behaves in the same way. It's going to insert itself with the nitrogen, insert itself with the hydrogen, and we end up getting products, nitrogen monoxide for the oxidation of the nitrogen, and water for the oxidation of the hydrogen component. And that's where we're going to stop for this week. So when we come back on Monday, we're going to start talking about how we use this information to start balancing equations. And that'll kind of set us off on that path toward getting us to the end of chapter 5, which is also the end of the chemistry intensive part of our unit here. So have a great weekend.